Welcome back. In the last part of this lecture, we'll be talking about finding all the solutions, so in other words, solving the trig equation over all real numbers, and we'll also be looking at cases where maybe we've got two different trig functions or maybe something that's quadratic in form. To start with, if we're looking to find all the solutions, then we're looking to solve over all real numbers from negative infinity to positive infinity. And actually, this is relatively straightforward to do because if you're looking at solving an equation that involves sine or cosine, you know that those functions have a period of 2 pi. So first find all the solutions within one full revolution, and then all the solutions that you find will be coterminal to those angles. So it'll be whichever angles you found plus any multiple of 2 pi. And that's what I'm writing here. I would say that if you had a solution that was some number x, then another solution would be x plus some multiple of 2 pi, 2k pi, where k is an integer. And if you look at all the possible 2k pi's that you could add on, those are all the possible full revolutions you could add on to that angle x. That would be all the angles that are coterminal to x. Those would be all the solutions. The only modification that we have to do is that if we're looking at an equation with tangent, just remember that tangent has a period of pi rather than 2 pi. So we only need to find solutions between 0 and pi, and then all of our solutions are the solutions that we found plus multiples of pi. So I'm going to start off with this. We're looking for secant of x equals to 2, which is, of course, the same thing as looking for cosine of x equal to a half. And if you're thinking about your special triangle, the 30, 60, 90 triangle, we know that cosine of pi over 3 is equal to a half. So we know one possible solution already. We know if we're thinking about the solutions for cos of x equal to a half, one of them would be found at pi over 3. And that's one of the places where cosine is positive a half. We also know that another solution would be found in quadrant 4. And that would have the same reference angle of pi over 3. That would be the angle 5 pi over 3. So there's two solutions here if you're looking from between 0 and 2 pi. X is cosine inverse of a half, and from that we found that there's the solution that cosine inverse gives us, which is pi over 3, and we found that there were two solutions. There was pi over 3, and that there was also 5 pi over 3. These would be the solutions within one full circle. And of course, anybody that's coterminal to these angles would also be a solution. So for example, if you're looking at something where we did a full circle and then 5 pi over 3, that would also be a solution. Or two full circles and also 5 pi over 3, that would also be a solution. And so what we can say then is if these two numbers are solutions, x being pi over 3 and x being 5 pi over 3, then you could say, well, pi over 3 plus any number of full circles will be a solution, and 5 pi over 3 plus any number of full solutions will be a full circle. So I have to specify that k here is an integer. And there we go. We've got our general solutions. That's what I found here, our general solutions to this equation. Now, in addition to general solutions, which is the way we can express all the infinitely many solutions, we also want to find 6 specific solutions, and you can do that just by picking 6 values for k. And each of those little equations that I have would give you 6 different solutions then. So for example, if you wanted 6 specific solutions, you could say, well, if x were 0, you would have pi over 3 plus nothing and 5 pi over 3 plus nothing. If k were equal to 1, you would have pi over 3 plus 2 pi, which is 7 pi over 3. You would have 5 pi over 3 plus 2 pi, which is 11 pi over 3. If k were 2, you would have pi over 3 plus 4 pi, which is 13 pi over 3. And you would have 5 pi over 3 plus 4 pi, which would be 17 pi over 3. And I could keep going as far as I wanted. And in fact, I could also do negative values for k being -1, -2. So these are 6 specific solutions. Those are the 6 that I came up with. Of course, there's lots of different answers here because this equation has infinitely many solutions. And those are the general solutions that we've given up front. Okay, so here we're looking at another solution to a tangent problem, and we're looking at 2 tangent squared x minus 6 equals to 0, which if you were to rewrite this and isolate your tangent function, first bringing the 6 to the other side and then dividing everybody by 2, you would find that tangent squared is equal to 3. And if tangent squared is equal to 3, then that means tangent should be plus or minus the root of 3. So in other words, we're going to have 2 solutions, or 2 equations rather, to look at. Tangent of x being positive root of 3, and tangent of x being negative root of 3. And for this, again, we know that we're only going to need to find solutions between 0 and pi, and that's because tangent has a period of pi. If you're looking back at the special triangle that we had on the previous screen, we know that tangent of pi over 3 is root 3 over 1. So tangent of pi over 3 gives me root 3. And that also means then that negative pi over 3 would give you a value of tangent being negative root 3. Now, we're looking for the general solutions, and so we need to find all the solutions between 0 and pi. So the one solution that we found here, pi over 3, that definitely is between 0 and pi. So pi over 3, yes, we're happy with that one. The other solution, the negative pi over 3, that's not in my interval. That's not between 0 and pi. So the equivalent angle that is between 0 and pi, remember that tangent is also negative in quadrant 2. So if I were to look at having the angle being two pi over 3, that would be another place where tangent has a negative value. So you could say, actually, instead of negative pi over 3, you could say 2 pi over 3. So we have 2 solutions so far. Pi over 3, that's our solution in quadrant 1. And of course, any multiple of pi added onto that would be a solution. Also, 2 pi over 3, that's our quadrant 2 solution, plus any multiple of pi, that would also be a solution. And there we go. Those are our general solutions. Pi over 3 plus multiples of pi, 2 pi over 3 plus multiples of pi. And then if you wanted to list 6 specific solutions, you could say, well, if x were 0, you'd have pi over 3 and 2 pi over 3. If x were 1, you would have pi over 3 plus pi, which is 4 pi over 3. If k were 1, you'd have 2 pi over 3 plus pi, which is 5 pi over 3. If k were 2, you'd have pi over 3 plus 2 pi, which is 7 pi over 3. And if k were 2, you'd have 2 pi over 3 plus 2 pi, which is 8 pi over 3. And you could continue going. Again, for any integer value of k, with that value of k, this will give you one value, and this will also give you one value that would solve your equation. So these are 6 of the infinitely many different solutions for that equation, 2 tangent squared x minus 6 equals 0. All right, so if you're looking at something where you've got not just a single trig function, there's a couple of things that you might see. One might be something where it's actually quadratic in form, something like this. 2 sine square x plus sine x minus 1 equals to 0. If you were looking at this, you could say, well, if I replaced sine of x with u, then I would have 2u squared plus u minus 1 equals 0. And that's something that I could factor if I really wanted to. That's an easy enough one for me to factor. So again, not too hard for me to do here. I'm going to factor looking for numbers that multiply to negative 2 and add up to positive 1. And that is plus 2 and minus 1. So factoring away, I find that this factors to give me u plus 1 times 2 minus u minus 1 equals to 0. So u plus 1 is 0, and 2u minus 1 is equal to 0. So you have two values for u. U is negative 1, or u is 1/2. Now, the one thing that we can't forget here is, remember that if you're doing a substitution, you are going to have to go backwards and find out what is the value for the original variable. We found out that u is negative 1, but we weren't interested in what u was. We were interested in x. U is sine of x. So actually what we really have here is that sine of x is negative 1, and sine of x is equal to 1/2. So actually we've got two trig equations now that we need to solve. So sine of x is equal to negative 1. And we know that there's one solution for that. If you're remembering the graph of the function y equals sine of x, we know that between 0 and 2 pi, that we have a y value of negative 1 exactly once, and that's at 3 pi over 2. So we know then that x here should be 3 pi over 2. Now for the other part, we're looking for sine of x to be equal to 1/2. And if we're thinking about the fact that our x will be sine inverse of 1/2, thinking about using your special triangles, you know that sine inverse of 1/2 would be using your 30, 60, 90, or your pi over 6, pi over 3, pi over 2 triangle. You'd find that sine inverse of 1/2 is pi over 6. And of course, you know that we're looking for solutions between 0 and 2 pi. And knowing that sine is positive in quadrant 1 and also in quadrant 2, that tells us that we're going to have another solution that will also have that reference angle of pi over 6. And that would be the angle 5 pi over 6. So that would be the other solution that we would have in that interval from 0 to 2 pi. So there we go. We've got 3 values in our solution set. 3 pi over 2. We have pi over 6. And we also have 5 pi over 6. Now, the other thing that we might see, in addition to something that's quadratic, we might see something where maybe there's more than one trig function, like two different trig functions together. So for that, maybe we'll need to use some sort of an identity to get rid of one of the trig functions. So this could be the Pythagorean identities, maybe the reciprocal identities. And once we've rewritten the equation, then we can go ahead and try to solve it. So something like this, we're looking to solve cos squared minus sine squared equals to 0. And for this, you actually could think about it in this way. I could say, well, I know that sine squared x plus cos squared x is equal to 1. So if you wanted to, you could say, well, actually, cos squared x is equal to 1 minus sine squared x. This is my Pythagorean identity, just rewritten. So that's my idea here. I'm going to take the original equation that I have, and I'm going to replace cos squared x with 1 minus sine squared x. So that cos squared x, I'm replacing it with 1 minus sine squared x. And now I have just a single trig function, 2 sine squared x. And there we go. Now I just need to isolate my trig function. And when I do that, I'll find that sine squared x is equal to a half, which means that sine of x is equal to plus or minus the root of a half. So positive root of a half, negative root of a half, which of course is the same thing as root 2 over 2 and negative root 2 over 2. And then we just need to find out what are the angles that solve this equation. Again, going back and looking at our interval, we're looking for all the solutions within one full revolution between 0 and 2 pi. And the more that we know, the easier this will be for us to do. We've done a bunch of these sorts of ones before. And so this one, finding where sine is equal to positive or negative root 2 over 2, this is not too bad. We know that sine of x being positive root 2 over 2, if you were using your special triangles, your 45, 45, 90 triangle, you'd find that there is one place where x is root 2 over 2, where sine of x is root 2 over 2, and that's at pi over 4. And for the other one, where is sine of x negative root 2 over 2? Well, that's at negative pi over 4. That's coming from our inverse trig function. So the inverse trig function, sine inverse, it gave us those two values, pi over 4 and negative pi over 4. Now we just have to find the solutions that are actually in that interval. The first one, pi over 4, that one is. And so if you're thinking about pi over 4, that would be one place where sine is positive root 2 over 2. You also know that sine is positive in quadrant 2, so another solution would be 3 pi over 4. As far as the other solutions that we find, the places where sine is negative root 2 over 2, one of these would be in quadrant 3, which would be at 5 pi over 4. And the other one would be in quadrant 4, which is the angle 7 pi over 4. So we're going to actually have 4 solutions here. X could be pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. And those are all the solutions that we have in our solution set. All right, one last one, and notice for this one there's no interval of solution given, which means we're going to be looking for all possible solutions. I'm going to start off with thinking about this one here. I've got cosine and a secant, and I know that secant is the reciprocal of cosine, so I could say that this is 4 cosine x minus 1 over cosine. equal to 0. And if you were to multiply everybody by cosine of x, you'd have 4 cosine squared x minus 1 equals to 0. And if you were to solve this, you'd find that cosine squared is a quarter, which means that cosine of x is plus or minus the root of a quarter, which is plus or minus a half. So we have two things that we'll need to solve. We'll need to find out where cosine of x is equal to positive a half, and we'll also need to know where cosine of x is equal to negative a half. Now, same thing as always, you're going to be wanting to think in terms of your special triangle here. We know that there definitely is a place where cosine of x is equal to a half. If you're thinking about that, that would be cosine inverse of a half. And using your special triangle, you can find out that that happens to be at pi over 3. For the other one that we have, which is at cosine of x being equal to negative a half, or x being cosine inverse of negative a half, we know that if one of the solutions that we found that gave us positive a half was at pi over 3, then the solution that gives us negative a half would be at 2 pi over 3. So another solution that we get here is 2 pi over 3. Now remember, we're looking for all of the solutions, and so remember what we need to do is, number one, start by finding all of the solutions within one full revolution, then add on multiples of 2 pi to all of our solutions. So there's two solutions that we found, one of them for where cosine is positive a half and one where it's negative a half. But even in one full revolution, we haven't found all the solutions, because in addition to pi over 3, where cosine is equal to a half, there's also a quadrant 4 solution, 5 pi over 3, where cosine is equal to a half. And similarly, there's places where cosine is negative, not just 2 pi over 3, the quadrant 2 solution, but also there's a quadrant 3 solution, which is 4 pi over 3. So we found that there's 4 solutions to this equation just within that one full cycle between 0 and 2 pi. And so that means that if you're looking for all solutions, we have pi over 3 plus any multiple of 2 pi. We have 5 pi over 3 plus any multiple of 2 pi. We have 2 pi over 3 plus any multiple of pi. And we have 4 pi over 3 plus any multiple of 2 pi. And so for all of these are all where k is any integer. And there we go. These are the infinitely many solutions that there are to that equation. So pi over 3 plus however many full cycles, 5 pi over 3 plus however many full cycles, 2 pi over 3 plus however many full cycles, and 4 pi over 3 plus however many full cycles.